Hello everybody, this is Dr. Christopher White and welcome back to part 2 of our walk through the lab exercise Earth's internal structure and composition. So in the previous video we were just talking about how geologists collected samples representing each of the 4 layers of the Earth, and now we're going to look at how that information can be turned into data that geologists can use to analyze the composition of the Earth. So if we look at table 1.3, you can see we have the 4 layers marked out: mantle, core, continental crust, oceanic crust. And for each layer, you can see we have a composition, and this is an average composition. So some, not, most samples will not meet this composition perfectly, but if you average them all together, this is what you're going to end up with. So for instance, you can see that the Earth's core is about 6% silicon, about 86% iron, and about 5% nickel. Notice all of these elements here have been grayed out. That's because they're not there in very large quantities, so they're not really worth thinking about. But for each of the 4 layers, you can see we now have this average composition. Now, another piece of information that geologists can come up with is, well, once we know what each layer is made up from, we have the average composition, and we know the thickness of said layer from geophysics, from part 1, from the seismic data, we can then go, okay, exactly what percentage of the Earth's total mass does each layer represent? So if we look at this information here, you can see we have our 4 layers: core, mantle, oceanic crust, continental crust. And you can see the core is about 32% of the Earth's total mass, the mantle is about 67%, the oceanic crust is about 0.6%, and the continental crust is about 0.4% of the Earth's total mass. So what does that tell us? Well, to start with, it tells us the core is obviously very dense, because although the core is large, it's not massive. And yet it represents 32% of the Earth's total mass. So that means whatever the core is made from must be very dense. And based on our analysis, we know it consists of substantial quantities of iron and nickel, which helps to explain why it's so heavy. Once again, we also have some silicon mixed in there, but we also have quite high concentrations of other lesser elements which will be there in large abundances, things like platinum, gold, rhodium, cobalt, etc. So that helps to explain to some degree why, even though the Earth's core isn't massive, it does have it does represent a very large proportion of the Earth's total mass. In terms of the mantle, well, the mantle is the thickest layer in the Earth's interior. It's therefore unsurprising that it represents about 67% of the Earth's total mass. And then we have the oceanic crust and the continental crust. The oceanic crust is about 0.6%, and the continental crust is about 0.4%. And the difference is between these two is essentially a result of the fact that the continental crust and the oceanic crust have different densities. So oceanic crust is mostly made up of denser basalt, whereas continental crust is mostly made up of, comparatively speaking, lighter granite. So you could also say, oh, well, hold on, isn't there more oceanic crust than continental crust? The answer to that is, well, yes, but you also have to remember that the continental crust is thicker. So in terms of the total amount of each, they're actually relatively close together, but it's the difference in the rocks that make them up, and therefore the density of them, that helps to explain why you have this slight discrepancy in what they represent to the Earth's total mass. So we now have these two pieces of information. So we have our average composition for each of the 4 layers, and we know what percentage of the Earth each of those layers represents when it comes to the Earth's total mass. So what are we going to do with that information? Well, what we're going to do now is we're going to produce a weighted composition for the Earth. And so for each of these elements, so in this case silicon in the mantle, we're going to use the average amount for mantle rocks. We're going to use the percentage that the mantle represents for total mass of the Earth, and we are going to use that to calculate a weighted composition for silicon. So how are we going to do that? Well, you'll be happy to know there is a sample calculation down here to show you the exact process. So in this case, we know from the average data that the mantle is about 21% silicon, and that information is from table 1.3. We also know the mantle is 67% of the Earth's total mass. So for our weighted composition, we're going to do the 21% from the average composition, and we're going to multiply that by 67 divided by 100, or 0.67. So we're going to multiply 21 by 0.67, and that's going to give us 14.07%. And you will then put that value in table 1.4. In most cases, please don't go beyond 3 decimal places. There may be a couple of times, so for instance, if you're doing, I don't know, potassium in the mantle, where you may have to go beyond 3 decimal places, you may have to go to 5 decimal places, but please, don't put in too many. It just clogs up the table and makes it difficult to grade. So by doing that, for each of these elements in the 4 layers, we are going to produce a weighted composition. So you're thinking, well, what do we use that information for? Well, then we're going to go to question 2, and we're going to do the final step. And we're going to use those to look at the Earth's bulk composition. So if we were to repeat the process that we use in table 1.4, and we did it for all the elements in the Earth and how they're distributed between each of the layers, when you added all those numbers together, it would come to 100%. And so that is called the bulk Earth. Essentially, it's the bulk composition for the entire planet. And so in question 2, what we're going to do is we are going to produce a bulk Earth just for the 8 elements that we are looking at here. So we've got silicon, iron, magnesium, calcium, aluminum, sodium, potassium, and nickel. And so how are we going to do that? Well, we're just simply going to add together the amount of each element in the 4 layers. So in terms of the bulk Earth composition for silicon, what we're going to do is we're going to take the value from this column, we're going to add it all together, and we're going to put the answer right there. Done. Very simple. And so this is how geologists come up with the bulk Earth. And the bulk Earth is quite useful to geologists because it gives us something we can normalize data to, which is when we're analyzing data, it gives us essentially a standard against which we can compare that data. And so that means when we compare data between different areas and different scientific methods, we can, make comparisons that we can compare against one another, so we can, try and be accurate in how we're doing things. Okay, so that's what we're doing for part 2. So in terms of part 3, we are looking at the differentiation of the Earth. So I'm actually just going to come all the way down so far. There we go, to figures 110 and 111. See here. So we know that when the Earth started off, it was essentially just a giant sphere of magma, which was referred to as the magma ocean. Now, what we believe, or what data has shown us, is that the majority of the material that went to form the Earth was from a type of meteorite which is referred to as a chondrite. So these chondritic meteorites, we're talking millions of them, maybe even billions of them, all combined together, all smashed into each other over time to eventually end up with this big sphere of molten rock, which is essentially the juvenile Earth. Now, this magma ocean was obviously dominated by silicate magma, okay? But the one thing about chondrites is that they are very rich in iron. And so the problem is that you can only dissolve a certain amount of iron in a silicate magma. It's like having a glass of water. You can pour salt into it, but after a certain point, you can't dissolve any more salt into it. Your water becomes saturated with salt. The same thing happened with the early Earth. So we have this big magma ocean full of silicate magma, and we have all of this iron, and it can only dissolve a certain amount of iron in it, and there's iron left over. So what's that iron going to do? Well, it's going to form what's called an immiscible liquid. And so what you had in the early magma ocean for the Earth is you had all of this silicate magma, and in it you had these droplets of this iron liquid floating around by themselves. And we're using the term immiscible in the similar way that you would refer to oil and water being immiscible. They won't mix together. So we have these droplets of iron liquid floating around in the Earth's mantle, and eventually one droplet will hit into another droplet to form a slightly larger droplet. That will then combine with another droplet, so become even larger. And over time, these droplets start coalescing to form bigger and bigger droplets until the droplet becomes so heavy that gravity will start to pull it down through the silicate magma ocean. And of course, where will it move it to? It will move it towards the center of the Earth. And so over time, you have this rain of these iron droplets towards the Earth's center, where they eventually begin to form the Earth's core. So that's where the Earth's core is coming from. Then, as the magma ocean continues to cool down, remember the magma ocean at this point is losing heat to space. So the magma ocean is steadily getting cooler. Eventually, it will get cold enough to begin precipitating, crystallizing silicate minerals. Now, obviously, it's still very hot, so it's only going to be able to crystallize out high temperature minerals. So it's going to start by crystallizing out the mineral olivine. And it's going to start crystallizing out olivine in very large quantities. So it's going to produce more and more olivine, and because those crystals are floating around in this nice warm magma ocean, they're going to keep growing and growing and growing, and eventually these olivine crystals are going to get so large that they can no longer be suspended in the silicate magma, at which point they too will start dropping under gravity towards the Earth's core. And so these olivine crystals will start to form a layer marked out here in green around the Earth's iron core. Now, as the magma cools down even more, eventually it's also going to start crystallizing out the mineral pyroxene, marked out here by the darker green crystals. They too are going to get larger, and they are eventually also going to become large enough to sink down towards the Earth's core. And so this is the formation of the Earth's mantle. And so the Earth's mantle is dominated by olivine and pyroxene. Now, as the magma ocean continues to cool further, it's eventually going to start crystallizing out a new mineral. It's going to start crystallizing out calcium plagioclase feldspar. Now, the thing about calcium plagioclase feldspar is that it is less dense than the silicate magma. So it won't sink, it will float. So when these crystals of calcium plagioclase feldspar start forming, instead of sinking towards the Earth's core, they float towards the Earth's surface. And so on the top of our magma ocean, you eventually begin to build up a layer consisting of these calcium plagioclase feldspar crystals. And that is eventually going to form a crude early crust. And then over time, the magma ocean, which is now stuck between the growing mantle and the growing crust, is going to essentially be converting the liquid silicate magma into solid crystals of either olivine, pyroxene, or plagioclase. And eventually we're going to end up with a situation like figure 111, where you can see we have our iron core, we have our big, thick olivine pyroxene dominated mantle, and then we have our outer crust. And then in blue here, we have the residual magma from our magma ocean, the stuff that's left over. It hasn't been turned into solid crystals yet. And by this point, our magma ocean is going to have a composition somewhere close to mafic. And this magma is going to sporadically break through this early crust, where it's going to pour out onto the Earth's surface in the form of flood basalts. Or sometimes maybe a meteorite will come in and it will smash the Earth's crust, and it will allow this mafic magma to once again rise to the surface and once again come pouring out onto the Earth's surface. And so this is going to result in the formation of big flood basalt domains. There's also going to be areas where we are going to get our mafic magma fractionating even further, and it's eventually going to turn into a intermediate or felsic magma. And they're represented in this diagram as these little pink areas. And so this intermediate felsic magma, well, it's going to be there in relatively small quantities. It's not going to be super common, but it is going to either get stuck at the base of the crust, or it's going to intrude the crust to form, granite or tonalite intrusions within the Earth's crust. Or maybe in some super rare circumstances, there will be enough magma where it makes it all the way to the surface and it's erupted onto the Earth's surface as well. Now, this is important because over time, when plate tectonics begins, these areas of felsic rock will eventually begin hitting each other and sticking together, and they're going to start forming the early cores, which will eventually become the continents. So, this basic process of splitting the Earth up into different layers is referred to as differentiation. So we took this totally homogeneous magma ocean and we ended up differentiating it into the Earth's iron core, into the Earth's olivine pyroxene dominated mantle, and then eventually over time we also ended up forming the oceanic crust, which is dominated by basalt, and the continental crust, which is dominated by intermediate and felsic rocks. So great, we've got that pretty much down. So what happened later is Victor Goldschmidt came along, and Victor Goldschmidt looked at the table of elements, the periodic table. So if we come down here, here we have our periodic table. And Goldschmidt looked at each element, and what he did is he studied them and he analyzed, well, under the correct circumstances, what does each element prefer to bond with? What does it prefer to interact with? And so by doing this, he actually came up with 4 distinct groups of elements. You have the lithophile elements, which are here in orange. You have the siderophile elements in this kind of red color. You have the chalcophile elements in green, and you have the atmophile elements in white. So you're thinking, okay, what does this actually mean? Well, if we come up here, you can see a basic description of what each group likes to bond with. So in the case of the lithophile elements, they really like to bond with oxygen. And so they're often referred to as the rock-loving elements because think about what rocks are made from on Earth. Silicates, SiO2, there's oxygen there. So a lot of these elements will be found in minerals in rocks. In terms of where most lithophile elements occur, they occur in the crust. They are more common in the oceanic crust and continental crust versus the mantle and the core. Then we have the siderophile elements. Well, they like to interact with iron. They're referred to sometimes as the iron-loving elements. And so in scenarios where there is no oxygen present or very little oxygen present, these elements will like to interact with the iron and they will go where the iron is going. Now, if there is oxygen present, oxygen gets in the way because the oxygen will naturally react with the iron and it will stop these siderophile elements going where they want to go. But in a situation where you have comparatively little oxygen, like the Earth's early magma ocean, these elements will want to move with the iron. Next, we have the chalcophile elements. These are sometimes referred to as the sulfur-loving elements, but they won't just go with sulfur. So if we just come down to the periodic table again, you can see there's sulfur, okay? But these elements will also follow selenium and tellurium as well. And so yeah, just like the siderophile elements, these elements will want to go with sulfur, tellurium, or selenium, unless there's oxygen around. If there's oxygen around, oxygen gets in the way. But once again, in oxygen-poor environments, these elements will want to move where the sulfur, the tellurium, or the selenium is. And then finally, we have the atmophile elements. They like to be gases. Okay, so we're talking about stuff that's mostly in the Earth's atmosphere. Okay, so Goldschmidt split up the periodic table into these 4 distinct groups based on how they react with different elements, or how they interact, should I say, with different elements. So why is that important? Well, think about it. We know that the Earth's early magma ocean differentiated into distinct layers. So we have this core, which is very iron rich. We have this mantle, which is silicate rich, but it's also quite oxygen poor. And then we have this oceanic crust and continental crust, which are comparatively oxygen rich compared to the mantle and the core. So what we can do is we can use the Goldschmidt classification of elements and we can think to ourselves, right, what would this mean during the Earth's differentiation? Where would these elements go as the Earth was splitting into its own distinct layers? So if we come down here, you can see we have questions 1, 2, 3, 4, 5, 6, and then we have 7 down there. We'll come to that. So questions 1 to 6 are essentially just trying to get you to think about where certain elements would end up. So a classic example are the Sigiophile elements. So these are the iron-loving elements. So think about it. They love iron. Which layer of the Earth's interior would they want to go into preferentially? Would they prefer to be in the core, the continental crust, or the mantle? Okay. So question 2, we know that platinum is a very rare mineral in the Earth's crust and mantle, right? So where will most of the Earth's platinum be located? Explain your answer. So in order, when you explain that, look at the Goldschmidt periodic table up here. What is platinum? Is it Sigiophile, lithophile, chalcophile? And think about where it's most likely to be in highest quantities. Next, question 3. The Earth's crust is oxygen rich. There is a lot of oxygen in the Earth's crust, and plus it's obviously in contact with the Earth's atmosphere, which also contains a lot of oxygen. So they'll be constantly exchanging oxygen between the two. So the Earth's crust is oxygen rich. So which class of elements will be most common in the crust? Chalcophile, Sigiophile, lithophile. Once again, when you answer that question, just come up here to the different descriptions for each of the 4 groups, and you should be able to come up with your answer relatively quickly. And then using the Goldschmidt classification, lists 3 elements that are likely to be enriched in the crust compared to the mantle. And there's a spelling mistake there. That should be and core. I apologize for that. Oh, what if I did it in lowercase? So list your 3 elements here. So once again, think about question 3. We know the Earth's crust is quite oxygen rich compared to the mantle and the core. What will that mean in terms of which group of elements will preferentially want to be in the crust? And therefore just think about 3 examples that would probably be in the Earth's crust in higher concentrations. Now in question 5, due to the oxygen rich nature of the Earth's crust, which 2 classes of elements will be unlikely to form bonds? Okay. Earlier on in this video, I'd said that there were 2 of the 4 classes that would find it difficult to form bonds if oxygen was present. Okay, so you should be able to answer that question. And then we have question 6, which is the Earth's mantle has little to no free iron. All right. So when we look at samples of the Earth's mantle, what we don't see are little droplets of iron by themselves. Any iron that's present in the Earth's mantle is typically encased or part of minerals. So minerals like olivine or a range of different oxide minerals. And so when we look at these irons, when we look at these mantle samples, it's not like the core. There's no liquid iron. There's no solid iron anywhere. So the Earth's mantle has little to no free iron, with most of it being locked in olivine and pyroxene, leading to it being classified as an oxygen-poor environment. Okay, so which class of elements are likely to be most enriched in the mantle compared to the core and crust? Okay, so think about it. Where would the Sigiophile elements like to be? Where do the lithophile elements want to be? And where do the chalcophile elements want to be? Bearing in mind that chalcophile elements really like oxygen-poor environments. So then we come on to question 7. And in question 7, you can see that we have 6 distinct samples of rock. And based on the samples themselves, and also a description for each sample, which contains information about the elements that are present in that sample, it's your job to try and work out which layer each of these 6 samples represents. The core mantle boundary, the continental crust, a chondritic meteorite, the mantle, or the oceanic crust. Okay, so a combination of this information and descriptions, the pictures here, but also the fact that you can compare those pictures to pictures from earlier in the lab exercise, for instance, the pictures in figure 1.9, will give you information about which part of the Earth each sample represents. Now, there's going to be one sample that has a chemistry that doesn't make sense. Now, remember, the Earth is differentiated. That means these elements are going to preferentially move into one layer over another. But one of the samples is going to have a mixture of elements that doesn't make sense. So it's going to have a mixture of sidrophile elements combined with a lot of lithophile elements. That shouldn't work, should it? Because lithophile elements love oxygen, whereas sidrophile elements, well, when oxygen's around, they tend to not be able to go where they want to go, which is with the iron. So that doesn't make sense. So where we have situations like that, what we're dealing with is material which is undifferentiated. So it hasn't split into layers. And so that will be your meteorite. That material will represent the stuff from which the early Earth formed before it differentiated. So one of these 6 samples represents a meteorite, and you're going to be able to distinguish that meteorite because it's going to have a very strange chemistry compared to the other 5 samples. And so you're going to write the sample letter in each of those 6 boxes, depending on which sample you think represents each layer. All right, so that should be it. So thank you for watching, everybody, and have a good day.